Hey there, Internet. Well, thanks for joining me on this fine day. Today, I want to talk about encoders, specifically current signal encoders. I just learned about them recently, and so I wanted to share what I found out. You might be in possession of one of these old encoders and have no idea how to use it. So, how did I get started on this journey? Well, I was on eBay and I saw what I thought was a really good deal on encoders. I found these Heidenhain ROD454M 3600 line encoders. Now, I have some optical encoders that are just kind of standard quadrature, and they're only 600 lines. So I thought these were, going to be great because they had so many more lines of resolution. What I didn't know was what kind of encoders they were. So, just really quickly, the different kinds of encoder technology and signals. I mean, the basic ones really are quadrature encoders. And quadrature encoders, they're very common in lower end stuff. And they put out square or semi-square high and low states on two different channels. You've got an A channel and a B channel. Based on essentially 16 different states that these signals can be in, you can figure out the position, or you can increment a position, meaning that you can step once in one direction or you can step once in the other direction. And to step in the other direction, you can look at which signal went high first, and that'll actually tell you which direction the encoder is turning. So here's just a little diagram of that. So you see up here, when the A channel rises first, that means that for this particular encoder and the way that it's wired is going clockwise. And here B rises first, and that's the way that you can tell that it's going counterclockwise. So there's a whole bunch of videos and information on YouTube on how quadrature encoder works. I'm not going to go into that. But what I do want to tell you is a couple of the other technologies that I newly became aware of. I'm not going to go into any of the proprietary protocols, but I think the next most common one is called 1VPP. And essentially what this means is you have a 1 volt peak to peak signal. That's going to give you the ability to either turn that into a digital signal. It'll give you the ability to do some interpolation, and you can slice the signal up into smaller pieces, as many as 400, and get much higher resolution. So these are seemingly this is a more modern standard. There's also differential encoders, which are going to be, in the quadrature world, it would just be a negative voltage that maps to both A and B, and you can use that negative voltage to cancel out any noise. I don't know if there's differential 1VPP signals, but anyway, the place that I found this particular bit of information was in one of Heidenhain's manuals. Now, the encoder I bought is this incremental sinusoidal current signal, and the giveaway is when you see this microamp SS sinusoidal signal. And that's what these Heidenhain encoders actually are. So there's two different signals. There's the sine cosine signal for the position, which is 11 microamps per, or peak to peak. And then there is also a 5 microamp peak to peak incremental signal that you should see once every 360-degree rotation. So that's what I actually had. And the giveaway is this 11 microamp sinusoidal signal, UASS. I wonder if they did that on purpose. Anyway, that's how, if you're looking at the manual and you see this in there, that's the kind of signal that you're dealing with. Now, there's little interpolation boxes that you can buy. These actually aren't that expensive. There's a lot of them currently on eBay. I saw a lot where you can pick up 4 for like $100, and these have different amounts of interpolation. So if you look at the specification, they'll carve up these signals into different chunks, as many as 400, and that'll give you a finer resolution on your encoder. Now, I could buy these, but number one, I don't have the cables. I don't know where to procure them. They seem actually fairly expensive on eBay. I'm not sure if this is a standard cable type, but I really don't want to make these cables. And I already have the encoders. So how do you decipher this signal? Well, what you need is a transimpedance amplifier. So if you look at the manual, this is the manual that actually came with the encoders. Again, you can see that you've got the 5 volts, which is these are radiometric, meaning the supply voltage has a huge impact on the actual measurement. This I1, I2, I0, this is your A, B, and index in current. And so you need to be able to take this current and turn it into a voltage. So they give you some help in the manual. And if you look on the page 9 of the manual, you see this little diagram, and this doohickey here is an op amp. So what you have here is you've got the signal going into these diodes. The photodiodes are going to create a current, and that's what's going to generate your I plus, your current plus, and your current minus. That gets fed into this op amp, which is configured in what's called a transimpedance amplifier configuration. And then they even give you the resistances here. So 100K for both of these resistors. The capacitors are 27 picofarads. This doesn't seem to be super critical. I mean, you can be somewhere in the ballpark. I've tested it with a couple different types. So I think if you're within 50% of this value, it'll probably work okay. This little circle here, this is the inverting. I think it's the inverting. Now I should go look that up. So I had to double check the meaning of this. It actually wasn't that easy to find, but this is the negative, as you see it on a diagram, or the inverting or the NOT gate, and this is the positive side. So they give you all the values, and if you use a 100K resistor, you'll get a sinusoidal voltage. Now, for a lot of the stuff I do, 3,600 lines per rotation is going to in a 4x quadrature mode is going to give you 14,400 pulses. Now, the upside of having more resolution is you have more resolution. The downside of having more resolution is your MCU is going to have to work a lot harder, and the interrupt frequency is going to be much higher. So I don't know that I actually want to have higher signal rates than 14,000 per revolution. That's going to add up to be quite a high amount of interrupts. So what I'm going to do in the configuration that I'm going to show you is I'm going to replace this with a 450 kilo ohm resistor. And what that's going to do is it's going to boost the gain of the op amp, and it's going to give a very square signal. So it's going to look much more like a digital quadrature signal. All right, so here's the circuit that I came up with. I'm not great at drawing circuits, so apologies. I'm going to try to walk you through this without assuming that you don't know what any of these symbols mean or what any of this is. The most confusing part about this diagram, if you haven't used any of these circuit diagramming tools, is the fact that I'm using a quad channel op amp. That means it can deal with four separate pairs of signals, and the way that these show up is as 4 separate op amps with the same name. So the part I'm using is an LM324AN, and I've kind of pulled this part apart so that I can kind of explain it in a bit of detail. So sometimes this tool drives me crazy. Anyway, so how does this work? So we've got our in this instance, I'm using the index pair of signals, but it works the same for all pairs of signals. So you've got a current signal coming in, and on the inverting side of the op amp that's marked with this minus, you have a resistor and capacitor pair. And what this is doing, the op amp will go into an oscillating mode without this resistor. I mean, without this capacitor. The resistor here is setting the gain for the op amp. So this is amplifying the signal. And on the positive side of the op amp, we've got another pair of resistor and capacitor, and that's connected to a voltage divider that's going to give us 2.5 volts. So the reason that we need 2.5 volts is that this signal will go from a negative voltage to a positive voltage. But if you're using a microcontroller like a ESP32, they don't know how to deal with a negative voltage. So what you have to do is you have to tie this the non-inverting side of the op amp to a virtual ground, and we're creating that virtual ground with just a simple voltage divider. So again, this is going to be 2.5 volts, and at the middle of our sine wave, right in the middle of the peak and the valley, is going to be that 2.5 volts on this side. On the other side, what that'll translate to is 0 volts to 5 volts on the output, and that's what we want for our controller. So what else is there to explain here other than, well, I guess the thing that you want to understand is if you want to change the gain, you have to change this resistor. So the higher value this resistor, the higher the gain will be. And if you wanted a sinusoidal signal, you'd use the value that they recommended. So that would be a 10K resistor up here on the inverting side of the op amp. If you want a square wave like I do, it's for the 5 microamp signal, it's a 1 mega ohm resistor, and up here for the other two signals, again, it's not really well laid out, but the other resistor value is 470K. I think this wire is wrong. This should go over here. Yeah, that's a big mistake. I was moving stuff around. Blah, blah, I gotta edit that out. So for this side, you want a 470K if you want a square wave on the output, and this is actually working pretty good. So, well, there is a simpler way to do this, and the most basic and most simple way to do this is literally just to put a resistor in parallel with your 2 voltages here, and that will give you that will translate the current directly into a resistance value. But again, the problem with that is you're going to have a negative voltage, and most microcontrollers don't like to have a negative voltage.
Hello, welcome to our short video on how to design.
So I found this video on YouTube. It was super helpful for helping me understand the way that this works in more detail. There's also some reference designs that they have that I think if you want to actually do the interpolation are going to give you a much cleaner signal. But we're not going to go into that in this video. But what we'll do next, we'll go ahead and jump over to the bench, and I will give you a quick look at what the signals look like on the oscilloscope and a demonstration of processing the signal with an ESP32. All right, so here's my setup. I know it looks like a bunch of jumbled wires. I've got the encoder cable here. Here's the encoder. I have another encoder set up here with the stepper motor, but that one's not actually hooked up to the signal processor right now. So I can just freewheel the encoder here. I've got a bunch of oscilloscope probes hooked up, and I have the signal split out also to my ESP32. Now, I can do a split cam on this, but I don't really think it's going to help a whole lot. So what I'm going to do is I'm just going to show you the waveform on the scope, and then I also want to show a pulse view of the decoded signal. So here, this is a paused view of the signal, the raw signal on the scope. And so you can see that the yellow channel here is leading, so that means we're going clockwise or counterclockwise. And then the blue channel is it's not quite in the middle. So like a perfect signal would be right here on this division, right in the middle of the rising signal would be right in the middle of this. I think my probe is not quite tuned right now. I think I need to just retune the probe, but I'm going to go ahead and whoops, I want to get it out of record mode. Let's turn this off. Okay, so this is what the signal looks like. Let me zoom out a bit. this is 2 milliseconds. So you can see that's turning counterclockwise, and if I turn clockwise, it's kind of hard to see here, but the blue signal is rising first here. And so from this signal, for each pulse generated by the signal, you can generate 16 points of position, non-interpolated. And when you actually have the pure sine wave and you do the interpolation, you got to use an inverse tangent function to do that, which is kind of math intensive. But anyway, that allows you to actually get even more, up to, right now it's 14,400 14,400 kind of clicks per revolution of position information, and that's 4 per pulse essentially. So multiply that by 400, and that's the kind of insane resolution you can get with the full interpolation, which we're not going to do. So anyway, that's what the signal looks like coming out of the op amp. And what I'll do next is I'll show you the view in Pulseview, which is kind of interesting. It gives a little more detail. So here is the view from the oscilloscope into this application called Pulseview, which is a logic analyzer. And if we zoom in, what you're going to see is for each channel, channel 1 and channel 2, that what we just saw is the yellow one and the blue one. The little squiggly line here, this is the analog signal, and then this square wave here is a processed, it's like a virtual Schmidt trigger processed logic signal. And the nice thing that I'm seeing here is, again, I think the probe on my oscilloscope needs a little bit of tuning, but this looks really nicely 90 degrees out of phase, which is what you want in one of these encoder signals. Now I plugged in a thing called gray code decoder, and this is very cool because it gives you a bunch of additional information. The first line is it's a phase count. I'm not really even sure what that is. Then we've got increments, which I also don't know what it is. This counts. This is actually the encoder counting. So if I were, and this capture is all going in the same direction, so it's all counting up. If I were moving the encoder right and left and right and left and right and left, it would actually be, the number would be going up and down. But this is the processed count. And then you can see the pulse time and the frequency of the pulses, as well as the averages of those. And then it actually translates that into an RPM reading, which is really interesting. I'm turning it by hand, but you see how much variation the RPM reading is here. So that's quite a big range from 27 RPM to 125 RPM. And I wonder if that's consistent throughout the capture here. Yeah, I don't quite know what causes that. I think the signals may not have the same, well, they should have the same period. Yeah, I have no idea what that is. If you know what it is, let me know down in the comments. But I think this view is pretty cool because it lets you go see the actual counts. It lets you see the frequency based on how quick that you might be spinning the thing, and you can pull it right out of your scope into your PC via an Ethernet cable and do some more in-depth analysis. This is the user interface for my electronic lead screw project, and in the configuration here, I actually have the ESP32 updating the encoder counts over WebSockets to a web interface, which is actually pretty cool. So I have this hooked up to the ESP32, and as I rotate the encoder, that's about a half of a turn, you can see the signal update. And so one of the tests that I did is actually it's really hard to rotate one of these super sensitive encoders by hand, but I hooked it up to a stepper motor and I ran it for I think I ran it for 1,000 RPM or 1,000 revolutions, and I got a very small number of error, less than 0.1%. So there is some small error in there. I'm not sure if the error is with the stepper or if the error is with the encoder processing on the Esp32 side. The Esp32 should be able to handle quite a high load. I think I calculated that at 800 RPM, it was going to be 192 kilohertz of updates. Now, this software is doing quite a lot of stuff. It's not only processing the encoder updates, but it's doing step generation, and it's calculating step sizes, and it's trying to figure out how fast the spindle's going, and then how many steps to take with the stepper motor to simulate a lead screw on a lathe. So it's quite intense on the calculation side. It's also got to do all the WebSocket logic as well, and so there's two CPU cores on the Esp32. It seems I have a kind of an approximation of the how the cores are doing, and if I spin this thing as fast as I can, it doesn't seem to be having much of an impact on the CPU utilization. That's it in a nutshell. That's how to take a Heidenhain current mode encoder and get a signal you can use with a Arduino or an Esp32 or some other kind of MCU. So if you have any questions, leave them down in the comments below. I hope this was helpful, and thanks for watching.